Okay. So we're very happy to have with us Courtney Bowman. Courtney he co-directs Palantir's Privacy Civil Liberties Engineering team, and he's very interdisciplinary in his interest and in his background, because he earned degrees in physics and philosophy at Stanford University, and he also worked as a quantitative and economic analyst at Google. And he, right now, Courtney works, as I said, in Palantir. Palantir is one of the most fascinating companies in the digital realm, and we're so happy to have him.
Thank you. So I find myself in the unenviable position of having to follow a wonderful keynote and a fantastic set of morning sessions, much of the content of which I think anticipates some of the concepts that I had hoped to hit on in this presentation. So I try to make this novel and interesting for those of you who have stuck around this afternoon. And hopefully we can kind of draw out some useful ideas that I think will further a little bit of our understanding about some of the issues around machine learning and artificial intelligence. And I should, by way of introduction, as a sort of starting point, I should mention the views that I'm going to express in the course of this talk are primarily my own, not necessarily the views that are espoused by the company I work for, Palantir Technologies, though there is a significant amount of alignment and overlap, which is one of the reasons that I work at that company. But just to say a few words about what Palantir does, what it is as a company. For those of you who are unfamiliar, we're a Silicon Valley-based software company. We build data integration and analytics software platforms. So we don't operate as a data broker or a data reseller. We're not a surveillance company. We don't collect information. What we do, however, is provide the data integration tools for institutions that have disparate large data holdings to bring that data together into a common analytical platform in which various controls and measures for accountability and oversight can be applied to ensure the consistent and responsible use of that data and the analytics on top of that. So when I'm talking to you about the limits of machine learning and artificial intelligence, I'm not coming at these issues from the perspective of someone who's solely steeped in the discipline of machine learning and artificial intelligence. Rather, we tend to think of these techniques as tools in the toolkit that enable certain use cases and applications. It's not a general panacea for all of the world's ailments, and I hope to demonstrate a little bit about why that belief that there are some fundamental limitations in these tools are so essential to thinking about their uses in appropriate contexts. So just to give you a quick outline of what I hope to cover in this talk, after my introduction, I'm going to give you a few definitions that I hope will give you a sense of some starting points that I'm drawing upon in terms of terminology throughout the course of this talk. I want to also draw some lessons from history. I'll be very selective in the historical cases that I draw upon and the characters that I talk about. But I think there's some very useful information that we can extract from prior interactions and prior experiences with a lot of these concepts. And then I'm going to delve into some insights that I think draw out a bit of the philosophical perspective that I tend to bring to bear on questions around the uses and applications of artificial intelligence and machine learning. I'm then going to say a few words about the technical considerations, actually more than a few words about technical considerations and practices that I tend to employ, that my team and my company tends to employ when we think about the viability of some of these techniques in the real world. And then I'll try and conclude with some thoughts to round out this talk. Just by way of definitions, I'm going to talk about a fair amount about artificial intelligence and the history of artificial intelligence, because I think those historical lessons provide us with some useful constructs to draw upon. And so when I talk about artificial intelligence, I think it's important to make distinctions between the traditional notions of strong AI or full AI or general AI, different terminology. And what I'm thinking about in terms of the notion of strong AI is this proposition that computers, when appropriately programmed, really are themselves minds or constitute the states that we associate with thinking or understanding. And I'm probably going to go a long way in terms of challenging that proposition, and drawing some lessons from that. Strong AI is to be juxtaposed with the notion of weak or cautious AI. And this is essentially the idea that computers provide useful tools. They tend to be very context specific, but the tools that computers provide us and the techniques that are programmed into those machines replicate certain capabilities that we typically associate with agency or agents that traditionally have carried out these actions. When I talk about machine learning, I'm going to typically be referring to the use of statistical techniques that give computers or machines the ability to progressively improve on specific, typically decision-making tasks. And so generally, I think of ML as a subclass of artificial intelligence. In a lot of this talk, I'll sort of use those terms interchangeably. If you want to challenge me on any of the applications of these terms later on, I'm more than happy to address those questions. And then I also want to bring out a concept from philosophy that I think is going to be very useful in terms of limiting the boundaries of what I think artificial intelligence is capable of doing. This is the notion of intentionality. And that is the idea that the property of the mind, the brain, by which it is able to represent other things. And I'll say a bit more about what intentionality means in context. Okay, so let's start with the history lesson. All of us should be familiar with the Turing Test or some variation of the Turing Test. Turing's formulation of the Turing Test harks back to 1950. And a particular paper, Computing Machinery and Intelligence, that Turing published. And the original formulation was in the form of the imitation game. So this was a game that you could play at parties. And the idea was you put people behind a veil, a man and a woman, and then you have an interrogator on the other side of the veil that can ask questions of those people. And the whole idea of the game, of course, is that the people behind the veil are trying to trick the interrogator to convince him or her that they are the opposite gender. And so the idea is that the Turing test, if you can replace one of those individuals behind the veil with a computer and end up with a success rate of deceiving the interrogator more often than a human participant, then you will have passed the Turing test. And this was essentially Turing's way of formalizing or representing an idea of can machines do or think the way that humans think, and to create this straw man representation. But my proposition here is that this is a rather anemic view of what it means to formalize thinking or understanding or intentional states. And so to bear that out, I want to draw heavily upon the work of John Searle, the Berkeley philosopher, who I think, I will assume many of you also have some degree of familiarity with. Searle, in a 1980 paper, represented or presented to the world his Chinese room argument. And the basic setup here is, let's assume you have a native English speaker that has absolutely no Chinese language capabilities or background. You put this individual in a room In the room, you have a set of blocks with Chinese characters. You also have a manual. So you can think of the blocks as a sort of database. You also have a manual that tells the individual to, when he receives an input, to translate that input into some response. And so you can think of that manual that the person in the Chinese room is interacting with as a sort of program. And so the idea is, from the outside, you feed in certain Chinese characters. The person in the room is responsible for translating those Chinese characters using the blocks of the manual into some output. And on the other side, someone receives a response to questions that are entered into the machine or the room that seem coherent. They seem coherent in the sense that they pass the Turing test. But the subtlety here is that if you take a step back and think about what's happening in this room, and you ask yourself the question, is the individual in the Chinese room actually doing something that we would associate with understanding Chinese? Do they understand the language of Chinese in any meaningful sense? And I think the normative answer here is no, they don't. They're merely following a program. They're following a set of tasks that they're asked to do. And so the question then becomes, if we find that the person in the Chinese room is not capable of understanding Chinese, why is it that if we were to replace the person with a computer essentially carrying out the same task, that we would associate understanding or intentionality with that machine? And I think that leads us to a conclusion that there's something that's fundamentally missing from this setup in the Chinese room. So to say, so the idea is that the person is capable enough of carrying out this routine to pass the Turing test, but we wouldn't say that they understand Chinese, just to be clear. So just to further clarify, in Searle's setup of the Chinese room, Searle is not claiming that all machines are incapable of thought, right? He's not going to that extremity. He's also not saying that no man-made machines are capable of thinking. So he's not trying to draw out expansive claims that we will never arrive at machines that are capable of replicating some form of intentional state or understanding or thinking. And in fact, we leave open the possibility because we know from millennia of history that humans are actually really good at building thinking beings. We have a rich history of doing this. We have babies, right? This is an idea of humans building thinking beings. In the literature, you can refer to this as wetware because the drool, and also this is sort of the concept. But the idea here is that there is something that is built into the phylogenetic contingencies, the evolutionary properties of creating these creatures that may be very difficult to simulate in a computing environment. And so Searle's formulation of this concept is to represent this as a bit of a category distinction, right? There's what we have in a machine is a set of formalisms. But these formal representations, this syntax or program for carrying out a certain task, doesn't carry the same intentionality. It doesn't contain the content or the semantics of what it is that we associate with the causal interactions with this world. And so this intentional behavior must be in response to real contingencies. It's not just formal simulations of reality that will somehow magically create this content. It comes from somewhere else, and thus far, machines haven't been able to replicate these capabilities. And the further claim here is that a programmed computer does not do information processing. It only is really manipulating formal symbols. And so that leads us to draw out some conclusions because I don't mean to make the claim that what we're typically talking about when we're talking about artificial intelligence in the context of these discussions throughout the day, I don't mean to claim that we're mostly concerned about strong AI. I think most of us have accepted that we're really just focused on particularized tasks for machines in navigating the world. But I do mean to suggest that some of the pitfalls of strong artificial intelligence also provide valuable lessons for us in understanding the limitations of weak AI. And so one of the things that we should draw out from this is that there's this whole world of intentional states that can't be obviated or outsourced to machines. There's some fundamentally irreducible qualities of thinking that cannot be replicated in the formalisms of information systems or computers. And those states are essential to the practical application of artificial intelligence in machine learning, particularly in highly sensitive environments in which oftentimes we're most concerned. So with that, I want to turn a bit more to some concrete representations of what I associate with the limits of artificial intelligence and machine learning. And the question I want to ask of us is, how should we think about computers and how they should be used for algorithmic decision making? And also, more critically, what are the types of decisions that may be appropriate to outsource to computers versus those where we make the decision that they're simply beyond the capability of what we think machines are able to do. And as a starting point, let me propose that a guiding principle we should bear in mind is the principle that computers don't understand. Okay, so I want to try and make that a little bit more concrete through a couple of examples. The first example should be very obvious to anyone who has taken any type of statistics. This is I love this example. New studies show 100% of criminals were once children, so reduce children and reduce crime. Right? It's comical, but it's there's something valuable to draw from here, because while it's a very reductive example, it speaks to some of the dangers of applying certain statistical techniques without also associating some level of understanding about what the data implies. And we can see in this example a very clear concept where causality may factor in, because we know that this single feature of people having been children at some point it leads to an absurd conclusion if you associate that with a causal implication of becoming a criminal. But this is analogous to the sorts of analyses that happen in data science fairly commonly, albeit it's a little bit harder to suss out when you have, instead of just one correlative factor, you have hundreds or potentially thousands, depending on the complexity of your system. Okay, so that's a very simple example. But let me give you another example of the limits of machine learning. And this is an example that's taken from a field of research called adversarial machine learning. And specifically, this adversarial machine learning applied to image recognition. So in image recognition, you have a corpus of data that you use to train a model to be able to identify certain types of images. Right? So imagine you have image one, a school bus, image two, a temple. And you've trained your model to be fairly effective or performative. We won't go into depth about the specific metric that you use to define performance, but let's just assume that you have a reliable metric. And you're really good at identifying school buses to 98%, whatever the metric is, and temples to 96%. So in adversarial machine learning, the idea here is that you can take some structured form of distortion and overlay it over the original image. And the consequence is that, and by the way, in this image, I'm really accentuating the distortion so that it's visible. The actual distortions would be hard to discern by by the naked eye. But the consequence is that you get these images on the right. And so the top image is what? This isn't a trick question. And the bottom image is also a temple. Okay, but the algorithm tells us that both of these are ostriches. Right? And it's not just saying that, yeah, I think these are ostriches. It's saying, yes, I'm certain that these are ostriches. But to us, as we look at this is an absurd conclusion, because we look at this, we can process what the image tells us, and we know that these images are what they appear to be. So something is lost in the formalized processing of these images, and I think that speaks to this point of something that's lacking in the way that machines process information. So another brief interlude of history. We have two characters, cognitive scientists on the left. Marvin Minsky is one of the fathers of artificial intelligence, one of the founders of MIT's AI lab. I raised these images in Minsky and on the right JCR Licklider because they present two conflicting images about what the future of artificial intelligence was likely to entail back in the 50s. Minsky had a sort of foreboding sense that artificial intelligence was going to lead to Terminator, Skynet types of dystopic futures, and a lot of the cautionary tales that he told are subsequently blamed for the AI winter of the 70s, this long period of a lapse in artificial intelligence development. But at the time, in the late 50s and early 60s, Minsky was prognosticating that within the span of 5 or 10 years, artificial intelligence was going to be taking over the world, and strong artificial intelligence in the way that I defined earlier. But contrast that with the vision of JCR Licklider, who's another kind of towering figure in computer science history. He's responsible for development of ARPANET, the precursor of the internet, and the development of the graphical user interface. Licklider presented us with a different notion of this idea of augmented intelligence, that humans would sort of set the goals and formulate hypotheses, but the routinizable work, the heavy lifting and processing that prepared the way for humans to apply their intuition and knowledge to develop insights from the information would come from the humans themselves. In the interest of time, I'm going to skip over an example of what this sort of human-computer symbiosis would look like, but I want to say a few words about what the framework that I think can be associated with an ethical approach to machine learning that bears in mind these historical lessons. One of the key insights to draw out here is that computer algorithms themselves, or by themselves, will not incorporate legal and ethical norms and societal norms that are essential to applying those systems responsibly, unless they're programmed to do so. And arguably, even when programmed to do so, that may not be enough, because there is this notion of intentionality that's so critical to achieving the appropriate ends. I do want to try and move very quickly through some technical considerations that I tend to associate as a framework for ethically approaching machine learning and artificial intelligence. And again, I thankfully can skip through this fairly quickly, because we've covered a lot of this content earlier in the day, and so we have internalized many of these lessons. But let me pause for a moment on the first issue, which is problem selection. And this is a recognition that not all problems are well suited for certain types of technological interventions. Use the classic example of Kaczynski et al., Stanford researchers, who thought it was a good idea to evaluate facial structures to determine sexuality. And you don't have to look back to history and understand the history of phrenology to know that this is a bad idea. There's something that strikes the conscience and calls out that this doesn't seem to be the right application for this type of technology. We see the dystopic results in the social credit scoring in China that emerges from these types of technologies. But one of the overarching insights here is that you have to ask these questions. Should you pursue a certain type of technology application, independent of whether or not you can, because once the genie's out of the bottle, it's very difficult to put back. I'm not going to talk about feature selection because I think we've kind of exhausted this in the course of the other day, but suffice it to say, feature selection is very difficult. There's all sorts of proxy variables that may be associated with sensitive categories, and even when you've identified all the proxy variables and the composite proxies, you still run into challenges of whether you need to preserve those features in the model in order to understand whether your model is including sensitive categories. But suffice it to say that these are challenging issues that need to be resolved, and oftentimes to resolve these questions, you have to look at the downstream consequences in terms of outcomes measurement. Sample bias, I'm also not going to delve too deeply into because this is well substantiated in the literature. We know from examples like the hand sanitizer dispenser that was trained only on white hands, or NYPD stop and frisk history, that if you start off with garbage data that's biased, you end up with garbage and biased results. But there are ways of addressing these issues through resampling or reweighting, or providing more complex analytical techniques that can get around those issues. Fairness, we have addressed a little bit, but I want to spend a moment to talk about outcomes measurements, because I think this speaks to one of the most vexing issues in the computer science literature. And that is that we're sort of at a point of crisis. We've alluded to this a little bit in the context of the Compass ProPublica debate, but the underlying issue is that you can constitute anywhere upwards of 20 or so different metrics or measures of fairness. And with very little algebra, you can demonstrate that any two or most pairs of these measures of fairness are fundamentally incompatible, which is to say, if you optimize on one measure, you cannot optimize on the others. And it actually gets even more complicated, because if you optimize on one measure at any given point in time, if the underlying conditions for your model change at a later point in time, you may not have consistent results. And so what this shows us is that for computer scientists who just want to know what fairness measure to use and what the score is that they should apply, the actual answer is much more difficult, because these aren't questions that can be resolved with a simple numerical response. There are some fundamentally irreducible properties that relate to the normative qualities of the notion of fairness. That fairness is not just about mathematical correctness. So lastly, say a few words about interpretability. I do think it is useful to tease apart the notion of interpretability in terms of understanding and deconstructing artificial intelligence, machine learning systems, to break it apart into the notion of a local interpretability. So interpreting in the context of an individual decision versus global interpretability of understanding the features and the underlying mechanics of a system. And then finally, a third notion of algorithmic interpretability, which speaks to the sorts of trade-offs that you might make in terms of making decisions about the type of fairness that you want to use or some other measure. So let me just skip to my conclusions because I'm out of time. The concluding thoughts that I hope to leave you with, none of these should be particularly profound, but they are worth reiterating. The first is that the real world is extraordinarily complex and changing. And the dilemma to that is that weak artificial intelligence and machine learning that I've been speaking to in most of this conversation, most of this talk, has a certain brittleness to it that doesn't mesh well with the complexities of the real world, particularly when you're dealing with soft notions that are intended to be subject to interpretation, debate, and discourse. Notions that don't lend themselves readily to quantification or reduction. And the consequence here is that algorithms and machine learning need to be recognized as tools, not as panaceas to fix all the world's problems. And once you realize these limitations of these techniques, what we're left with is an enduring role for human culpability and judgment in figuring out what the appropriate legal and ethical trade-offs are in the use of these technologies. And I will stop there. Thank you very much.
Okay, thank you so much. This was fascinating. And when I was asked to comment on Courtney's presentation. However, given that I haven't heard it before, I assumed that he would talk about his company, which is Palantir, and about predictive policing. So this is what I'm going to talk about. I think it's a fascinating issue because Palantir has been in the news, probably not necessarily justifiably for some of the issues. So what I'm going to relate to are two general concerns that might arise when you have private companies using data in order to engage in predictive policing on the one hand, and on the other, I'm going to talk about governance by data. I'm going to be very quick in order to leave some time for question. So I'm going to raise two concerns that I think we should think about in this world. So the first has to do with market power concerns. And I want to highlight here the tension between the analytical ability of firms and the market power that they might have. Because Palantir is a private firm which provides the government with very important services, and it does so probably very well. It organizes the data for police stations around the world, around the US, and that it also provides analytical services. So given its success in providing these important services, it has expanded the services into many counties and states around the US. And its ability to do so was based partly on its comparative advantages relative to other firms. And so one of the concerns is that the government might be locked in to Palantir or to some of its tools, and the reasons might be first mover advantages based on learning by doing of data analytics, develop better algorithms based on more and better data provided over years by the government. And again, if a new firm wants to enter, it would not have access to that data until it wins the bid, because you won't give data which regards policing to any private company. That creates a high barrier to entry. Transfer learning, once you learn from one data set, you can transfer it to another data set. That also gives Palantir a comparative advantage. Scale economies, when you win bids over many police stations around the US, and also intellectual property concerns. If you've already organized the data in the past in certain formats, and you have intellectual property over those formats. So what's the problem? Again, this is not saying in any way that Palantir does not provide top-notch services or important services. What I'm saying is that a heavy reliance on one firm, which has such market power, might be problematic with regard to, and create high prices and not enough investment in innovation. And in such situation, it's difficult to rely on market forces to create incentives. And again, I'm basing part of what I've said here on interviews that Wired has conducted with police departments, which have said that Palantir has spiraling prices, hard-to-use software, opaque terms of service, and failure to deliver products. So again, I have not checked Palantir. I'm basing it on BuzzFeed and Wired and others. Again, this is a very general claim. You can find a similar claim, or you can make a relatively similar claim with regard to any other firm which has control over important data, okay, which cannot then be easily copied by others. The other concern that I want to talk about, and again, I'll do that as quick as I can, relates to innovation concerns. What happens when the government uses data which is collected by private firms in order to govern? It might be predictive policing, it might be setting bail, it might be what other people talk about with regard to personalized laws. They all come under this realm. This is based on an article that Neva and I have written together. So just very briefly, if you look at the data economy is based on three basic parts: data collection, and then it's synthesis and analysis, and then it's users, and it actually has a reciprocal element, because once you have data about users, you can then use it in order to create a better algorithm, so you use the data in the system. Now, what happens if you have governance by data? You have the use of the same data by the government. You have the same inputs. You have the data and the algorithms. And what happens when you have potential dual use? So again, the same system, but now you have a governmental use as well. And the argument that we're making is that once you add a governmental use, you might change a collection, you might change analysis, you might change private use in ways that you have to take into account. And you might have some distortions, data subject. If people know that the same data is going to be used by that is collected by private firms, is also going to be used by the police, for example, this adds another dimension by potentially increasing law enforcement or placing higher legal burdens on citizens. And the harms then become not only harms to people as consumers, but also harms to them as citizens. And that harm is strengthened by the government coercive powers and this strength of potential sanctions, and by the fact that you have a lock into government. While it is much easier to change a product or a service, it's much more difficult to change your government, okay, or to move away from it. So if that is true, that might create distortions on the conduct of suppliers in many ways. It might create distortions with regard to collection. They might not be able to collect so much data, or will not want to collect so much data if data subjects are going to react to such data collection. This might lead to reduction in the quality of the data which would be collected. And here, Professor Nissenbaum's really important work is really important, because if you know that your data is going to be used to govern you by the government and not only by the markets, you might not provide it, or you might obfuscate it, or you might do anything that would create noise in the system. And that, of course, would affect the products offered and the data-driven innovation. I'm not going to say more of that. If you want, you are welcome to read. I just wanted to make these 2 points. Thanks. Now, let's open it to questions. Neva?
Unaccountable factors that may create conflict or undermine your algorithm. Recognizing that those deficiencies may exist, I think forces you as a company or institution that's employing these technologies to keep some kind of finger on the dial.
Nefit, sorry.
Fascinating talk. I think these kind of discussions always take us to science fiction, so excuse me for doing the same. But I've been thinking about movies like Her and Ex Machina. I wonder to what extent the intention is really essential over time. Because at the end of the day, we're all humans and we adapt. And if we see an artificial intelligent machine that looks like humans and acts like humans and feels like humans, maybe at some point we wouldn't even care about the existence of intention. So I'm just curious to think, like, to what extent do you think those technological limitations will be kind of remembered and perpetuated over time when humans will get more comfortable with machines that look and feel and act like humans?
If we can take a few more questions, maybe for time, Helen.
This is just a human in the loop question. It seems like it's a question of scale, because the other day I was backing out, I've got a new car, and it overrides me all the time. So I was backing out, there was a snowbank, I knew that it was okay to just like bash into it, but the car just suddenly braked. So it's sort of, somebody's making a decision about the machine overriding the human without necessitating the human in the loop. And I don't know, just curious if there's some principled way of figuring out the taking over part and when it's okay.
One last question because of time, Rita.
AI scientist. I want to defend AI here. They kind of look at it as like it's a closed problem. That's it. This is the state of the art, and that's it. We were not going to improve. And also, your examples are kind of tricky. The example that you gave with the children and criminal, this is a trivial solution, and most current solutions, machine learning solutions today, will not come up with this trivial solution. Very easy way to avoid it. Adversarial examples. Yes, it's a problem, but I would say it as a limitation. It's a problem, an open problem, I agree. But I believe that we will solve it in a day or two, or a year or two. And also the same thing with this machine. They're stupid, they just started. You know, if you look at the phones, I don't know, all the technology like 20 years ago, we didn't think about the solutions that we have now. So maybe it's a bit too early to think about the solutions, you know, and at the level that we have now. So something that already established, yes, but you know, with the car, and I know I have the same car, and it's annoying, but I believe that the self-driving car will have enough information, and it's much more clever and sees around, sees the road and all the satellites, and has more information. I'm not saying it's going to be good at the first try, but it's going to improve. And the last thing I wanted to say, about biases in the data. Yes, this is a real problem, and the problem is not only what in the data, it's not what in the data. Well, I have many examples, but we don't have time to share. And it is but humans should do something like this. Think about algorithms, how to engineer the data for the machines. And the last one is utility versus privacy, utility versus fairness. So this is a problem that's not related to machine learning. It's a problem related to any decision-making process. So I don't know why we're blaming machine learning. You know. So as I said, we had this conversation before. If you can define this, I can put it in my algorithm. So the problem is the definition. How do we define it?
Can I?
Yeah, sure. 2 minutes.
Let me try and cover at least some small facet of each of those wonderful questions. Your question, I think, reminds me of one of the threads that I pulled out of Helen's talk earlier, which is that I think we will find that these technologies are emaciating our interactions more than they are elevating our expectations. And we will reduce the way that we interact with these machines. You see this in in examples of care robots for the elderly. There's something that's being lost in those interactions. The thought of having my grandmother walking around with a robot that can't really carry on any meaningful conversation. There's something that's really pricks the conscience about that. I think and I guess the other facet is to get to one of your questions is this closed problem of AI. So I'm not claiming that it's a closed problem, that none of these issues can be resolved. I think some of them can be resolved or refined. And I think adversarial AI is a good example where we may continue to develop a system to a point where it addresses historical maladies. But the point of it being an adversarial framework is that you always have an adversary on the other end that's testing the boundaries. And so there are continuous ways of defeating it. And you may come to a decision at some point that the system is good enough. And I think that comes around to one of Helen's questions about what's the principled way of making determinations about how we override these systems. And I think that's something that we have to talk about and come to a communal consensus around. Mm-hmm. And maybe part of that is process driven, where we complain enough to the manufacturer of our vehicle that we're comfortable with the car intervening in certain circumstances, but they absolutely need to fix this backup camera thing where I'm going to hit the snow, otherwise I'm going to get out of the car and just walk. So I think these are things that we will have to negotiate, and I think that also speaks to one of your other questions about the utility versus privacy, utility versus fairness set of trade-offs. You're right that what computer scientists or AI researchers want is some answer about what the right trade-off is going to be. I don't think there's a mathematical way to determine what that trade-off should be. It's a societal question that we need to work through policy and political discourse. It's not something that we're going to magically pull out of a formula.
Great. So I agree that what we need is some kind of overriding button or stop button. Okay, so I'm pressing my stop button for this wonderful session. Thank you so much.
Excellent. I just want to, I have some few comments. Yes, one shout out.